Hello, I am still alive and I'm feeling better than my last recording where I talked about the powerlessness of we the people versus tyranny and pedophiles and just all of this evil stuff. I don't think we're powerless, but I do want to make a little comparison of like how much power the people actually have these days compared to the power that is accumulating at the top. Because due to technologies, anyway, I just want to make it like a kind of a graph that shows like technological advancement versus the power that comes through like education and being informed. And that's the power that we the people have, as opposed to technological advances, which largely get distributed at the top. So anyway, we'll do that later. For now, we're going to talk about quantum gravity. So I'm listening to this book about it, and there was this interesting comparison that was made about how for most of human history, like up until like the 1600s, I believe, somewhere in there, when optics were developed, the smallest resolvable thing that we could see was like the breadth of a human hair, right? And then we finally invented like microscopes, magnifying glasses, microscopes, getting down to like electron microscopes, and now we're in the age of particle accelerators, and all of that work has basically made it so we could perceive something like the size of the human hair to on the scale of like 10 to the negative 16 centimeters, which is roughly the size of a proton, I guess. Although I feel like it should be more like 10 to the minus 18, because we were able to detect gravitational wave fluctuations that was even in the same book. So anyway, let's just say 10 to the negative 16 centimeters is the scale we're currently at. And quantum gravity is expected to really come into play on the scale of like 10 to the negative 35. I believe that was the number, centimeters. So like logarithmically, we're not even halfway there yet. Like if we, like it just boggles my mind that things can get that small, right? So I was thinking about that, and I was like, oh yeah. And then also the other comparison was like, with current particle accelerator technology, in order to probe that small of scale, we would need a particle accelerator on the scale of a galaxy. Because you need to put more and more energy into something to decrease its wavelength, so it's actually capable of resolving something as small as 10 to the negative 35 centimeters. So anyway, bearing that in mind, I was thinking about this other thing, which I was reading in Feynman Lectures, Volume 3, Chapter 12, 13? I don't know. But it's on hyperfine spectral lines, right? So you know spectral lines where atoms emit light at only discrete like frequencies of light. So you can like use an interferometer to look at the sun, and you can see the spectral lines, and you can see like what elements are in the sun without even going there. And in fact, we discovered, I believe it was helium, which is why it's Helios, the god of the sun. We discovered that on the sun before we discovered it on Earth, due to those spectral lines. So using basically just like a a prism sort of apparatus. You can split light up into a rainbow sort of thing, but if you look in close enough on that rainbow, you'll see little bands of light, and that is the light being emitted from these atoms, okay? And the way that that happens is because electrons are orbiting the nucleus of an atom, and there's different orbital shells, different distances that an electron can orbit around an atom, and they have to be on one of those distances exactly. They can't be like halfway between. So an electron has to jump all the way out to the next available distance or all the way in, and that distance is, well, it has to be exact and can be made up for by the energy of a photon. So jumping in and out of orbitals can absorb or emit a photon of a particular wavelength. And the wavelength of a photon is how much energy it has. Anyway, so there's that sort of, there's those sort of spectral lines that go through, but the hyperfine lines that I was reading about in Feynman's lectures were, or are, the lines you get because not from an electron jumping out a distance, but instead from the spin of an electron. So an electron can be spin up, it can be spin down, and protons can be spin up or spin down. And so the example used in the lecture was that of hydrogen. So we only have one proton and one electron to consider. And so the proton can be spin up, spin down, electron can be spin up, spin down. So there's 4 different states there of concern. I'm ignoring everything else. And I thought it was really interesting because these different configurations of spin, you could both have them spin up, you could have one spin up, one spin down, vice versa, or both spin down. These different configurations of spin have different energy values, or at least one of the states does. So that means that without an electron even moving outward, by just flipping the spins, there can be an energy difference that can absorb a photon of a certain frequency or emit a photon of a certain frequency. And anyway, so at the beginning of the lecture, Feynman was like, this is on the scale of 100 millionths the amount of energy that is typically released during an electron jumping in and out of its next orbital or whatever. So like this is like a very tiny amount of energy, 100 millionths that amount of energy for just flipping the spin, and yet we can detect that in distant galaxies just from like redshifts and stuff. And so you go through the lecture and it goes through to calculate that amount of energy, and it turns out that the frequency of the photon that is emitted from the flipping of spin, that's it, just the flip of the spin of the electron-proton pair, is 1.42 billion cycles per second. So this frequency of a photon is oscillating at 1.4 billion times a second. And I was like, that's insane. That seems like so much energy. That seems like that is oscillating so fast for something that supposedly has very little energy. That's like blowing my mind, right? And so then I was like, well, that's the wave frequency, but what's like the wavelength? Like how many oscillations are there, right? And I was like, well, there's 300 million, light travels at 300 million meters per second, and we times that by 100 to get it into centimeters, so 30 billion centimeters per second, and this is oscillating at 1.4 billion times per second, so 1.4 billion times goes into 30, what is that? Basically twice, 20 times, I should say. So it's a little more than 20 times. So that means that it's 20 centimeter wavelength, right? It goes 300 billion centimeters, but you divide that by how many individual oscillations there are. So for one oscillation, in one oscillation of light, it goes 20 centimeters. So then I was like, that is on the scale of like the resolving power of that light. That means if you shine that light on something, it would get really blurry. If the thing was bigger than 20 centimeters, the light could just completely miss it. And so I was like, okay, well, what kind of energy of light would we need in order to resolve something on the scale of a graviton, quantum gravity? And so if that is 20 centimeters, we need to be able to draw that back to an oscillation that's happening every 10 to the negative 30, 34 or something, 35. Which means that the frequency needs to be, instead of 20 centimeters, it would need to be 10 to the 36-ish times more energetic. 10 to the 36th times more energetic than, I mean, this is just a number at this point, right? But more energetic than these hyperfine transition energies, which I think is on the microwave spectrum. I know that like your microwave at home is like on the scale of like a few inches or something, an inch or two wavelength, something like that. So imagine that, but times 10 to the 35 times more energetic, because the more energetic a photon is, the faster it oscillates. So it shrinks the wavelength, but we need the wavelength so it oscillates basically twice right together within 10 to the 33, 10 to the negative 33 centimeters of distance. So it really has to be bunched up. You really got to load it up with energy. I don't know. I just thought this was a fun little calculation, because they're both over there making comparisons in two separate books about energies and things. And I thought it was kind of fun to come in and make comparisons between the two books and be like, yeah. So that's why you don't want to use light as your medium for measuring quantum gravity, because I wonder, it seems like it would be a ridiculous amount of energy. I don't even know if it's possible to have that amount of energy in a photon, or if it would just turn into a black hole. Anyway, so that's all we talked about, was just some good old Good old quantum gravity. Just running some calculations, having some fun for once. Okay, having fun. And anyway, I'll see you later.